Okay, hello everyone. Today I will be teaching you about register, the Morris menu classic model of a bus. As you can see, here we have a simulation of a bus, how it works, with all the registers lined up. Now, here we'll toggle with the bits D7 and I bit. D7 that is IR 15 to 12th and I bit that is the 15th bit. Now let's say we meet the D7 bit 1 and IR bit 1. As you can see, if D7 is 1 with IR 1, it will activate IO mode. Here you can track all the active RTL informations. Now here let's see the IO information, IO operations. Let's see, we want to perform AC to INPR. Here you can see the first step, PC to AR. The RTL been actively written over here. Let's do the next step. The next step, fetching the instruction from memory to IR and then incrementing PC. Again the next step, that is the loading the 8-bit input from INPR to AC bit 0 to A7. Here as you can see, all the 3 steps have completed, and here we can view the final values of INPR, that is 65, and the PC, that is 257. Like this, in this simulation you can even toggle all the bits. As you toggle the bits, here you can see the active transformation of bits is noted down. Then you can see all the idle performations in the ALU, all the instructions being performed over here. Here you can see there is memory reference instruction, register reference instruction and IO. This will activate based upon the D7 and I bit values. Now this was a normal form. Let's go to the AR mode. Let's switch our screens. Okay, hello my fellow viewers. So as you can see, we have switched to the VR mode. This is the pointer. The pointer is placed well in between the index finger and my thumb. If you want to see any register information, you can sort of just take the pointer to that register and you can see the active bit information there. Now using the pointer, if you want to select anything, then just you sort of pinch. On pinching, if you see the pointer turning red, that means the thing is selected. Now let's perform some instructions. Say I want to flip my D7 bit and I bit first. So let's make the D7 bit 1 with I bit 0, that would be the register reference instructions. And let's say I want to flip a memory bit. So I'm flipping the memory bit. Yes, I have flipped the memory bit, and one more. Let's say I want to flip the IR bit. Yes, successfully done. Now let's select the register reference instructions and say I want to perform this instruction in particular. Skip if AC equals to 0. As you can see, as we have selected the skip if AC equals to 0, the SZA register reference instruction, the first step is performed. Here you can see the active RTL language going on, and you can clearly see what has happened. There is a transfer to the AR. Now let's say if you want to move to the next step, then just show your palm. On the show of your palm, you would be able to go to next step. Again, next step. Okay, you can see what has happened, that the accumulator was 0, so the instruction has skipped. So the instruction has been completed. You can see a complete message over here. Similarly, in this system, if you want to increase the speed of the atoms, the classical bits, then you can just show the 3-finger sign. The 3-finger means speed up. So now let's show the palm, and you can see the bits moving with much more speed. And if you want to go back a step, then you can simply select it from here. Yes, it's selected. So you can either step forward, backward, or reset the bits. Really, you have the freedom of whatever you want to do. Now you can see that you can select from a number of categories, that is the 3, the memory reference, register reference and the IO instructions. And this was our classical system. So if you want to reset the whole system, then just show your both the palms. As you can see, gesture 2 palms open, that means reset. So this was the system for classical bits, but this video is really for how the COA would be reimagined if we had a quantum system. How would be the registers, how would be the movement of qubits, that is the quantum bits. So before starting with the qubit system, there is some kind of basics I want to give my audience. So let's switch to our quantum system from the classical system. Okay, so before moving on to the quantum bus, what really a quantum bus is, there are few concepts of quantum system which we need to clarify so we have a better understanding in the future. So let's start. I'll explain you some topics which would be really needed for the quantum bus. First being qubit versus bit. As you can see on the left hand side, this is a classical bit. A classical bit can exist in one of the two states, that is, it can be either 0 or 1. Well, on the right hand side we have a qubit. Now this sphere kind of formation, this is called as the Bloch sphere. I'll spell it out for you, B-L-O-C-H, a Bloch sphere. And this inner projection moving, we can measure the rotation of the qubit by help of this projection. Now you can see a qubit always is denoted as A0 plus B1. The 0 and 1 are variable, they can change. But the alpha and beta, that is the complex numbers, the complex entities, they always exist. Now you can see that 0 and 1 are written in a special kind of encased brackets. Now this is called as the bracketed notation of the quantum system. Whenever you are dealing with quantum system, you have to always represent the bits in this bracketed system. You can see the upper half of the Bloch sphere is in position 1 and the lower half is in 1. The upper half is in 0 and the lower half it is in 1. So this means there exists 50-50 chance of the bit being in 0 state or 1 state. Now keep this in mind, as further it will blow your minds what this really means. Without further ado, let's move on to the next topic, that is the superposition of a qubit. Here you can see the projection moving inside the Bloch sphere at 0 and 1 state. As the projection moves, it makes this kind of wave. The upper half called the constructive interference and the lower half the destructive. Together it is called a coherent wave. You can see the superposition is denoted via this formal equation. Now this wave changes on the position of the projection of where it is in Bloch sphere. The qubit forms this wave, constructive and destructive. Remember these terms as we'll be using them in future. Moving on to the next topic. Wait, before moving on, superposition, I'll define it for you. Superposition is a phenomenon where a qubit can exist in either 0 state, 1 state or both. Just imagine, it can be 0, 1 or both 0 and 1 at the same time. How mind-boggling is that? Now as we have tapped on this button, it is to measure the system collapse. And why the superposition collapse when we measure it, we'll cover it in the further concept. For now, just keep in mind, superposition is being at either one place or the other, or being at both the places at the same time. Moving on to the next topic, that is the quantum entanglement. Now this is my favorite concept in the quantum system, entanglement. Let's say I place a qubit in my palm on Earth, and I place the another qubit on top of Mars. Now if I make a change to the qubit on my palm, the qubit is entangled to the other qubit which is on the Mars. That means whatever change I make to the qubit on Earth will also affect the qubit on Mars, and this is irrespective of distance. Even if there is infinite distance between the two qubits, the entanglement would be there. Just imagine how mind-boggling it is. If we are able to fully understand entanglement, then imagine the communication we can have. We can communicate using qubit irrespective of the distance, without any network, without any cell, just by measuring the different entangled state, by measuring the entangled system. So this is the equation that shows the entanglement. You don't need to memorize it, but just you can look at it for once. So this is called as the fully entangled state. There is also another state called untangled state, but we do not need to bother ourselves with so much theory. So just see this. Now why there is a plus here? Because this is a plus state in the entanglement. There is also minus state, which simply induces a minus sign here instead of a plus. But again, we do not need to bother ourselves with so much theory. Now let's go on to the next topic, that is the no cloning theorem. Now there is a theorem called no cloning theorem that says that we cannot clone the value of a qubit exactly, because just imagine, I told you that the qubits are in constant superposition. How can you clone a thing in time which can exist in two states at once? It's nearly impossible. So as the theory is written, that it is physically impossible to create an identical copy of arbitrary unknown quantum state, and it was proven by two scientists, they were German scientists, Wouters and Zurek, in 1982. So this is the no cloning theorem. We cannot clone the theorem, but swap between the qubits works, and that is achieved by using a number of C0 gates. What is C0 gate we will see in future. It is the next topic in fact. So just keep in mind, we can swap the quantum bits but never clone them. Now we'll move to the quantum gates, the first being Hadamard gate. Now for watching this video, there is a basic understanding that the viewers need to know about quantum system, but if you don't know, then don't worry, I'll explain you them in brief. Firstly, the Hadamard gate. Let me just change the slide. The Hadamard gate is represented as this: 1 by root 2, 1 by root 2, 1 by root 2, and minus 1 by root 2. This is the Hadamard gate, and the Hadamard gate exists in two positions. That is, if the input is 0, it exists in the plus state, and if the input is 1, it exists in the minus state. Now what this really means, you do not need to bother yourself with that. Just remember the plus and the minus state that the Hadamard gate exists in. Now coming on to the second gate, that is the poly X gate. Here the poly X gate is nothing but there are poly X, poly Y, and poly Z gate, X, Y, Z being the axis. So poly X gate just symbolizes the rotation of the qubit. As you had seen in the Bloch sphere, the position was constantly rotating. So using the poly X, Y, Z gates, we can kind of invert the axis and measure the qubit on that axis. Next being the C0 gate. Now C0 gate is a very important gate which you need to remember also in the future. C0 gate is called as the controlled NOT gate. So basically what C0 gate does is, there is a target and there is a control bit here, a C0 gate. This is a very accurate description. Just a second. Yes, so in C0 gate, this plus sign, as you see, this is the target bit and this is the control bit. C0 gate, just remember one thing: if the control bit is 0, then you just write the output as it was. But if the control bit is 1, then you flip the target bit and write the control bit as it was. Further is the Toffoli gate, that is the CC0 gate. So basically Toffoli is an advanced version of the C0, just adding one more C in front of the C0 already existing. So based on the position of this first 2 qubit, this is a 2 qubit state gate, a 3 qubit state gate. C0 is a 2 qubit state gate. So in the Toffoli gate, based on the position of the first 2, based on the values of the first 2 qubit, you measure the third qubit. So these are the gates. Then the swap. As I mentioned earlier, the cloning of qubits is not possible, but swapping is. Now how we achieve that? By using C0 gate. Now in this video, I won't be explaining how C0 gate is used to swap the bits, because that would be really time consuming and we have to also cover up the qubit bus. But just keep in mind that to swap the bits we use C0 gates. Then the QRAM, the quantum random access memory. So this is a bucket brigade tree. It is operated in O of log n times and it is broken into 12 levels. 12 levels can represent 4096 words, that is 2 raised to 12 equals to 4096, and this is also used in the Grover's theorem that searches in root n time complexity. Really fascinating. As you can see, the upper bit, the first ever bit here is the first bit that stores the 12, that is the 2 raised to 12. Then further down it is broken into 2, 4, 8, 16. So like this it is broken down and it will be at 12 levels. So 12 levels would be sufficient to express 4096 words. Then quantum measurement. As I had told you to remember that it is impossible if we calculate a quantum system, if we measure a quantum system, then the superposition collapses. Now why is this? Now carefully listen to the words I say. Let's say that a quantum bit exists for a time t equals to 0 to t equals to 5. In this t equals to 0 and t equals to 5, the quantum bit would be in constant superposition. That is, it will be in state 0 or state 1 or constantly in state 0 or 1. Now let's say at time t equals to 3, I want to measure the state of the qubit. At t equals to 3, I try to measure the state and it comes as the qubit is in state 0. Here the superposition has collapsed. Now why so? As we have calculated it, the superposition collapsed because we know that in superposition the qubit can be at 0 or 1 or both. So we measured it at a constant time, at a particular time. So the superposition really diminished because at time superposition cannot exist at constant time. It will be either 0 or 1, whatever state it is in. So we say that when we measure the quantum bit, the system collapses to either 0 or 1. Then next is the decoherence. Now as I had explained you in the previous slide that the waves formed coherence and decoherence, this is a visual diagram for it. You can see decoherence is basically the loss of quantum information due to the interaction with environment. When the qubit interacts with the environment, it is so sensitive and fragile in nature that it loses some information due to the disturbances in the environment. So here you can see this stable wave is formed, but it's not really this stable. When it will enter into the decoherent state, then it will again become a very kind of shredded wave. Then next is the reversibility. Reversibility means that quantum system is fully reversible. Now this is a very important topic which you want to keep in your mind, that if we are looking just at the output of a quantum system, we can completely trace back the input. This is not possible in classical bits, but in qubits, if you look at the outputs, if you have the output, then you can trace back to the input. How fascinating is that? Now I could give you some example, but that would again really stretch the video. So let's keep it for another video, that how we say that a quantum system is reversible. So as in the information it is written that the quantum bus replaces AND with Toffoli gate, the inputs are preserved. This is mandatory for quantum error correction. So as I said, by the output we can trace back to the input, and vice versa, the quantum system is called as reversible. Now these were the topics I wanted to have clear for you viewers before we moved on to the next, the quantum bus system. So you can just reverse the video and watch all the topics again if you want to have a more in-depth understanding of the Q-bus. Now this, my friends, is the quantum bus system. Now one by one, let me explain how this is different from a classical classical bit register bus. So if you are really watching the video till now, almost after I guess 15 to 20 minutes, that means you are really interested in the quantum system, and thank you for watching till now. So let's start with the quantum bus without any further ado. What I'll do is, there are certain instructions, I'll execute them and explain you with help of the theory which I explained you in the past. Now first one, AR, the PC swap to AR. Let's execute this step. As you can see, the bits moving from PC to AR. But you remember the no cloning theorem by Wouters and Zurek, right? That stated that no unitary operation can satisfy this operation because of the no cloning theorem. So this violates the linearity of the quantum mechanics. Therefore, the quantum bus cannot copy the PC to AR. It must swap. Now, as we know, for swapping we use the C0 gates. By implementing a C0 gate logic, we can kind of swap the qubits and not copy them from one register to other. Then further, that each C0 takes a 40 nanosecond on the superconducting qubits. So this operates in total of 120 nanosecond. Now here in the side information bar, you can see the theory. You can compare how it is different from the classical bit to quantum bit, and you can see the advantages and disadvantages. I'll note down the website link in the description. I won't read out the whole thing, or else the video would become 1.5 hours long. So I'll just mention the basics which you would need to understand each of them. The second one, the QRAM AR to IR. As you already know, in the past we studied the QRAM, the quantum RAM, that is a 12-level system which passes on structured information from first level to the 12th level, and it is capable of storing 4096 words. So that is really used here. So QRAM was proposed by a scientist called Giovannetti, Lloyd and McCoon in 2008. It is a very new topic to the world. It generalizes the classical RAM interface to accept a superposed address register. A classical AR holds only one fixed address, which is M outputs one data word and IR latches it. But a QRAM, a quantum RAM, it accepts a superpositioned address. So all data words are loaded simultaneously. So after the loading is done, I'll execute this step again. As you can see, from memory to IR. As this loading is done, the IR is entangled with AR. This joint state encodes the entire memory concept. As I've explained you the concept of entanglement, here you can see the AR to IR, the bit is entangled. There happens an entanglement between the qubits. That means that whatever change occurs in the AR qubits is simultaneously fetched into the IR qubits. So this really does our work. Next step, that is the Q increment PC to PC. Here, as you execute this step, simply in the PC you can see the waveform forming. So the program counter must advance to the next instruction address after the current instruction is fetched. So classically, a ripple carry incrementer adds 1 to the 12-bit PC values. The carry propagates from bit 0 up to upward. This would have O of n, the worst case delay. But in quantum, the PC may be in superposition. So representing all execution paths in parallel, the quantum incrementer that is made from a cascaded C0 and Toffoli gate adds 1 to every basis state simultaneously. So instead of the classical system which incremented each bit individually, here all the qubits existing in that state are simultaneously incremented. This explores all the program paths simultaneously. So what we are talking about here is exponential increase in the calculation time. it will reduce the time complexity exponentially. This is what the Groove's algorithm is based on. It helps us calculate the searching in root n time. So this is the real advantage where it lies in the quantum system. Next thing, the IR, the 0 to 11, the address bits to AR again. So IR to AR. Now what happens here, that the instruction register, the IR holds a 16-bit words, the bits 15 to 12 being the opcode, the 4 bits, and bits 0 to 11 the memory address. In classical, the lower 12 bits of IR are wired directly to the 12 lines of AR through the bus. This is purely combinational, no clock edge needed, and there is zero propagation delay. But in quantum IR, it is in superposition over instruction words. So to copy just the address field into AR, we apply 12 C0 gates. Now this is where a disadvantage of the quantum system comes. As we cannot directly clone the bit by the no cloning theorem, we need to swap the bits, and for that we would need 12 C0 gate. Now remember, a control NOT gate is very expensive for a quantum system. So using 12 of them would be very energy draining. So we apply 12 C0 gates, one per qubit of the address field, each controlled by corresponding IR qubit and targeting the AR qubit. And this is not a full swap. Remember, as the address field remains in the IR only, the opcode is untouched. We do not touch the opcode, as it will be I beg your pardon, as it will be used in the future to kind of decode the instruction the memory IO or the interface instruction. So this is not a full swap, and it is controlled fan out of 12 qubits. After this setup, the AR will hold the same address field superposition as IR 11.0. So what basically this tells us, after this happens, the AR will store the same superpositioned state which IR had, and this is not done by cloning, but this is done by 12 individual C0 gates. Then the next thing, that is the QRAM. Again we see the concept of QRAM, the QRAM AR to DR. Once again, the QRAM AR to DR. Now T4 fetches the operand from memory. As we know, the operand, the bits 12 to 15, it fetches the operand from memory. Now AR holds the operand address that is decoded from IR 0 to 11, the address that is decoded. And in the classical system, what happened, that AR derived the memory address lines, memory output MAR, and the DR latched to the 16-bit data value, one operand per cycle. Now in quantum, AR is in superposition over operand addresses. So there is a superposition between the AR over the operand addresses. The QRAM loads all. The 12 level system QRAM it loads all corresponding data values into the DR simultaneously. So again, the use of C0 gate would be there, as we are swapping the bits from one to other. Now AR and DR are now quantum entangled, so they both are in entanglement. The joint state AR cross DR, the cross you can see, it is called as the Krochner's product. You can just search what Krochner product is. It encodes all address operand pair at once, measuring AR equals to K instantly, and forces the data register to become the memory address of K. Now this entanglement is the basis for quantum associative memory, a resource with no classical analog. So what it really says is what quantum associative memory is. You can search, it is a whole topic as a whole. Right now we'll be moving on to the further instruction, that is the Toffoli, and that is the CC0 gate, AC and DR to the AC. Here you can see the DR to AR and AC and DR, there was an entanglement. What here happens is, classical AND is irreversible. You cannot reverse what happened. But we had learned that quantum state is fully reversible. From the outputs you can trace back to the inputs. you can reverse back to the inputs. So in a classical AND, it is irreversible. 2 input bits is 1 output bit. Given output equals to 0, you cannot determine if input was 0, 0, 0, 1 or 1, 0. It can be any of that. The information is destroyed. This violates the quantum mechanics where all evolutions must be unitary, meaning reversible. The quantum equivalent of this is the CC0 gate. Of the AND gate, the quantum equivalent is the Toffoli, the CC0 gate. Here we can kind of derive the input from the output. So the result A dot B in the register, inputs A and B are unchanged, that is they are reversible to cover A dot B and discard inputs. So here once again let me perform it. From DR it is moved to AC, and then there is an entanglement between the DR and AC. Once again for the last time we will see it. Okay, now the last one, that is the Draper add ACDR to the AC itself. Now in the classical edition, it used a ripple carry chain. A carry would propagate from bit 0 to 15th. It would be O of n depth. The worst case relay scales linearly with register width, meaning as the width of the register, as the size of the system would increase, the time complexity would increase in the worst case. Now the Draper adder, the Draper 2000, that is, it performs addition in the Fourier basis. Now for this you need to understand the quantum Fourier transformation. So QFT is basically mapping of frequency of qubits along with their position. If you don't know what QFT is, you can just search it up. It's a really easy topic, would hardly take 5 minutes, and you can understand what QFT is. Coming back, so the we apply the QFT to the B and it transforms to the frequency domain. As I said, that QFT is to kind of map the frequency of the qubits along with their position. Then apply the controlled phase rotation. So once again, rotation is done by the Pauli gate in whatever XYZ direction we want to do, and then we apply the QFT and the on the plus state, that is the inverse transform recovers A plus B mod 2n. Here no carry chain, that is a complexity of ON square is there, single qubit rotation gate. The key advantages is there is no carry propagation delay. In the classical bit there is a propagation delay when the carry was generated, but here that is not the case. Each bit's phase is updated independently and also operates on superposition of all AC DR pairs simultaneously. So the quantum Fourier transformation plus state, that is by the controlled R gate, phases to QFT-B, and the A and B gives us A bracket A plus B mod 2 power 16, that is the 16-bit address. The mathematical part, if you don't want to bother yourself, you can just ignore it. But yes, I think we are done with all the execution steps. So this really what we studied was the quantum bus system. I may be wrong at some parts because a quantum bus system is not really discovered by us. It is not possible to be built as of now due to lack of mechanics and our partial understanding in entanglement. As of now, we are not able to kind of control the entanglement. But if you want to really study more on this topic, then there is a paper of IEEE, a conference paper of IEEE on the quantum bus, how a quantum bus would be existing if it would be there, along with the mechanical implementation. So if you want to really understand this topic in depth, you can just see that video simply and understand. It is on the official IEEE website. You have to just search that quantum bus using the quantum mechanics by IEEE. So this was all for the video. For the website part, I'll be uploading the website link in the description box, and if you have really any doubts or suggestions that you want a video on some other topic, then just type it out in the comment box. And yes, we'll be seeing you soon with another knowledgeable video. Thanks for staying tuned.